Live from the BBC, The Naked Scientists.
Hello and welcome to this week's Naked Scientists with me, Dr. Chris Smith, and with Dr. Katani.
Hello!
This evening, tsunamis, supervolcanoes, quakes and shakes, because we're bringing you a show that really should rock tonight. Boom, boom. It's the geology of natural disasters, volcanoes and earthquakes, that kind of thing. To help us out with it, we have from the Open University, Janet Sumner. Good evening, Janet.
Good evening, Chris. Hi.
Thank you for joining us tonight. We also have from University College London, Tiziana Rossetto, who's a structural engineer. Good evening, Tiziana.
Good evening, Chris.
Now, obviously, one of the things you'll be able to help us out with is the old saying that it's not earthquakes that kill people, but buildings.
That's absolutely true.
OK, and so you've been out there to Pakistan, so you're going to be telling us a bit about that tonight.
Yes.
OK, and also here to tell us a bit about what volcanoes put out into the atmosphere is Tamsin Mather.
Hi there.
Good evening. Thank you for coming in. If you have any questions for any of our guests this evening, the phone number's 08459 25 2000. If you're calling internationally, it's 44 for the UK, 1223 25 2000. And you can also send me an email, chris@nakedscientist.com.
Right, and also coming up on the show, we have some really good news. This is the good news I've been waiting for. Scientists have found what's good for you in chocolate. Yes, it's good for your heart. I'll be telling you about that later. Yes, thank you, God. Chris will be bringing you stories about the science of Schadenfreude, who finds pleasure in revenge. And it may not be the answer you expected. And also we'll be talking to Professor Donald Brownlee, who's at the University of Washington. On his desk, he has the Stardust capsule that I talked about last week, which has been thousands, millions of miles out into space, has been sweeping up particles from a comet and has brought them back down to Earth. It landed safely last week, and we'll be hearing from him about what's inside. Chris.
And of course there's our competition, science fact or science fiction. It's very easy. We give you a couple of scientific facts. You have to tell us if they're true or if they're false. And up for grabs tonight we have, from the Wiggly Wigglers last week, your own worm composting kit, which is worth about 90 quid, and some vouchers to give away. So if you want to have a go at winning that, just give us a call now, 08459 25 2000. And if you fancy doing a bit of home experimentation and a tabletop volcano is your cup of tea, then get together a bottle of fizzy drink. Lemonade's a good one, but Coca-Cola will work too. And you need some mint imperials or a big jar of sugar. So get those things, and we'll be going to the Naked Science Laboratory with Derek, who's there today with Herbert Huppert and with James F. Stathew to find out how to do this week's experiment. And remember, if you're first through on the phone with the correct observation and explanation of tonight's experiment, you could be walking away with a fantastic prize. 08459 25 2000 is the phone number for any questions on anything to do with science, technology and medicine, which we'll slot into the show where we can, or you can email us throughout, chris@nakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Welcome back. I have got some good news for chocoholics everywhere. Hands up in the studio, who's a chocoholic?
Definitely.
Right, we've got 4 women, 1 man, 3 of us love chocolate. Well,
Tell you what, Kat, Janet actually has brought in a Cadbury's cream egg, which she has given to me because she wants to use it to demonstrate the principle of something volcanological. What is their proper word? Volcanological. Is that a word?
Yeah, volcanological. In fact, I'm not a chocoholic. I'm the only one who didn't put my hand up, and I have to use these wretched things all the time for my experiments, and I can't eat the evidence when the experiments go wrong.
I'm sorry, Janet, but I've eaten it.
I'd like to know who in the studio is a Vulcan. I think there are some pointy ears under the
and fingers. So I've just seen Tamsin sort of dividing her hand in the Vulcan hand. Sorry, you can carry on with your story now.
Anyway, yes, good news for those of us who do love chocolate, because some scientists who are from the University of California have been studying Cuna Indians in Panama. Now, hot chocolate actually developed in South America, and the Indians used to eat it. It was a very spicy hot chocolate then. But they found, by studying Indians who still live on their island compared with Indians who move into Panama, Indians who live on their island, they drink loads and loads of chocolate. They drink about 4 cups a day of hot chocolate. And once they move to the city, they only drink about 4 cups a week. And they found that the people in the city had much poorer sort of heart health compared to the people on the island. Now, this may be because the Cuna Indians are living on this lovely tropical island compared to living in the city where it's really horrible. But they studied the chocolate and found that there's a chemical in it, a flavanol, which is one of these good chemicals in wine and stuff like that, called epicatechin, I think. Someone correct me on that. But they actually found that this chemical has an effect on your heart, on your cardiovascular system. It loosens up your blood vessels, which is better for you and prevents the likelihood of heart attacks and strokes.
And this is an antioxidant, is it?
Yeah. And also they found that if they give that chemical just to people instead of the chocolate, it also has that effect. So it's probably not quite so fun. But yes, chocolate is good for you. It's got to be cocoa-rich chocolate. You want your 70% cocoa chocolate.
Sure, because a common argument here is that chocolate, whilst touted as containing all these antioxidant chemicals and is therefore good for your blood vessels, at the same time packs an enormous energy punch. And so if you were to go eating all this chocolate to give yourself this rush of antioxidants to mop up all these nasty things in the bloodstream, you would be gaining a terrific amount of weight, because chocolate is about 50% fat by weight, isn't it?
Yeah, it's loads of fat and sugar. So, moderation is the key, and really good chocolate, I reckon. Really dark, quality chocolate. That's probably good for you.
Now, here's a story that'll bring tears to your eyes, and especially if you're a woman, it seems. Tanya Singer from University College London has been looking at the science of sympathy. She fooled male and female volunteers into playing games with a group of tricksters, and she then brain scanned the volunteers as they watched their tormentors apparently receiving agonising electric shocks. Female volunteers, though, seemed to be willing to forgive everything. Their brains registered only signs of sympathy, but the men's brains told a very different story.
What we do is investigating empathy, so that's brain responses to the pain of other people, okay? And what we wanted to know is whether these brain responses to the pain of other people change as a function of whether you like or dislike someone.
So how did you do it? What was the actual paradigm you used?
So we knew that using economic games is very potent to induce liking and disliking of people. So in these games, each subject engaged in monetary exchange game with two actors, and now the subject could send money to this actor. Now one actor would always reciprocate the trust of the subject by sending high amounts of money back, and so engage in big cooperation. And the other actor would always cheat by sending very unfair amounts of money back and keeping most of the money the subject sent them to themselves.
So very quickly, the subjects would have become or developed an intense dislike for the cheater.
Exactly, because humans really, really dislike to be cheated on, and they really like, on the other hand, to engage in cooperation.
So then, once you'd nurtured these intense sensations of dislike or intense sensations of liking for the actors, what did you then do to work out whether people's empathy could be changed?
So the subject could now see either the fair player or the unfair player getting pain delivered through little electrodes attached to the hand of the player. So now what we could measure is brain activity while the subject was perceiving the fair or the unfair player getting painful stimulation to their hand.
And what was the outcome? Were people generally less empathic to people who had cheated on them?
The surprising bit was that women showed empathy for fair and unfair player, but the men showed a total absence of these pain-related empathy response to the unfair player. But instead, they showed an increase in activity in areas which process reward.
So the men were almost being satisfied by seeing the person getting their just desserts then?
Exactly. So the men basically showed what we call Schadenfreude. It's a satisfaction to see someone suffering you dislike. And that was also surprisingly correlated. So the more that men expressed a desire for revenge, the higher the activity in this region were in men.
Why do you think it's just the men?
So that's a very good question. I mean, we had expected both to show these responses, women and men. It might have been because the mean of revenge is a physical mean here. That's a painful stimulation. And it might be that in evolutionary terms, men have favored physical threat, and women perhaps would take more of a psychological revenge. So if we would have allowed to, for example, give punishment points, perhaps women would have given the same amount of punishment points. But women actually don't really like revenge in terms of physical threat.
Simply shocking. Tanya Singer from University College London explaining why men seem to be nature's troublemakers. But then I'm sure our wives will still forgive us nonetheless.
The Naked Scientists. Supported by the Wellcome Trust.
You are listening to The Naked Scientists on BBC Local Radio in the Eastern Counties and also across the world through our podcast available from nakedscientist.com. And we've had an email here from Lewis de Messiah, who's in Dubai. So we've had emails from all over the place. We've finally got some in from the Far East, had some in from Hong Kong. And Lewis says, hello, Docs, I'm from Dubai in the United Arab Emirates. He has downloaded all our podcasts and has listened to every single one. So that's all our mistakes, chaos, and loads of good science as well. And he wants to know if we're ever going to do a video podcast in the future for our experiments. What do you reckon, Chris?
Well, that's the problem with being the naked scientist, isn't it? That
You don't want to risk any acid burns in an unfortunate place.
I have to get a much bigger microphone than I have already.
Yeah, we'll have to get a widescreen lens, won't we? For your beer gut.
I haven't got a beer gut. I'm slim. If you want to have a go at our experiment this week, remember, it's kitchen science. All you have to do is take part in the experiment, have a go, see what happens, and then call in with the correct observation. If you're the first through on the phone with the correct answer, you could win yourself a prize. We've got some fab prizes tonight. We have a Win Your Own Wormery. This is from the Wiggly Wigglers. You put things from your kitchen in the wormery with some worms. They eat it and turn it into this fabulous worm juice that makes your plants grow like the Amazon rainforest. So if you want to have a go at winning that, just have a go at kitchen science, or you can ring in for our competition, Science Fact or Science Fiction. We're going to go now to our laboratory, where Derek is with Professor Herbert Huppert and with James F. Stathew, our experimenter this week, and they're going to be finding out what you can do with a bottle of fizzy drink and some mint imperials. Hi, Derek.
Hi there, and welcome to the Naked Scientist Laboratory once again, where we'll be making actually a mini volcano of our own this week in the lab. Now, before we get started, I must remind you that although we're not in a kitchen this week, you can do this experiment in your kitchen, and preferably in your sink at home. You'll be hearing more about that in a moment, but believe me, it's a really easy one this week, so keep listening for the details. Now, with us this week to explain the experiment is Professor Herbert Huppert, no less, from Cambridge University. Hello there.
Good evening, how are you?
Excellent. So please do tell me a little bit more about what we're going to be doing in this experiment.
Well, what we're going to be doing is investigating some of the important ingredients in explosive volcanic eruptions.
Fantastic. And this is Herbert's first time with us on The Naked Scientist, but the first of many, I do believe. So thank you very much for coming to do this with us. And also, even more importantly perhaps, a fantastic helper who's here. So could you please tell us your name and age, please?
My name's James and my age is 10.
Thank you very much indeed. And it's great to have you here. And you're going to be doing our experiment today as well. Lots of great science then. So science, what do you like about science?
Space.
OK, and what kind of things about space do you like?
Orbit and stars and planets and things.
OK, well, thank you very much, James, and we've got the experiment ready for you to do very shortly. Now then, you at home, this is a spectacular and very easy experiment, and all you need is the following, OK? You need a freshly unopened bottle of some kind of fizzy drink. Lemonade, Coke, whatever. That's fine. 2 litres preferably in a nice, simple, circular bottle, OK? You also need some mint imperials and, if you've got it, a Smarties tube. Now, if you don't have mint imperials or a Smarties tube, then you can just use some sugar, all right? So I'm betting that most of you at home have got some of these things, right? But we're going to hear about what to do with those in a moment. The only other important point is to do this in the sink, and believe me, you'll find out why. Anyway, Herbert is here to tell us what to do with all these things and to tell James how to do it. So, Herbert, what do we do?
Well, James, take the Smarties packet, and you've emptied it of all the Smarties, and you've also cut one top off, so you have a long tube that's open at one end. Then you take the packet of Imperial Mints, open it, and then pour as many Imperial Mints as you can into the Smarties tube.
OK, so here we are then. We've got a load of Imperial Mints ready for you and a Smarties tube. So could you get some in there, please? And maybe tell us how many you're getting in there as well. All right, I think that's about full. How many do you think that is?
13.
OK, well, we've got something like 13 Imperial Mints there. What's next?
Now you bring them over here to the sink, in which you have the lemonade bottle, and you open the lemonade bottle, and it fizzed just a little bit. That's because it has dissolved carbon dioxide. That's to make it taste good, and it comes out of solution. Just a little bit, though.
OK, then, so we've got the lemonade bottle opened and there's a few bubbles in it. Now, we're not going to actually do the experiment right now. We're going to wait until the second half, and we want you to do it at home. But, Herbert, what should people be doing at home?
What they should be doing is taking the Smarties tube and pouring the Imperial Mints into the lemonade bottle.
Right then, yes. And, of course, the point here is that we've got to make sure all those mint imperials go into the lemonade very, very quickly, all at once. So that's why we've got the Smarties tube set up there. And also, of course, if people may not have mint imperials at home, so they might want to do it with sugar, for example. So what can they do there?
Well, they could make a funnel out of paper and pour 1 or 2 largish tablespoons of sugar into the lemonade.
Excellent. And I suppose the important thing is just to make sure that it all goes in at once. So either, with a funnel made out of paper or an actual funnel, just get those 2 tablespoons of sugar, pouring it all into the lemonade all in one go. And then you have to tell us what happens, because if you've got the right answer, you can win a prize. So one way is to call us on 08459 25 2000, or also if you want to email, that's chris@thenakedscientist.com. And there's some amazing prizes there ready for you to win. So please get on with that. Get your lemonade in the sink, in the bottle still, of course, and get those mint imperials or sugar into it and tell us what happens. OK, then, so before we go back to the studio, James, I wonder if you could tell us, what do you think is going to happen when we pour all those mint imperials into the lemonade?
I think it's going to fizz and all go out.
OK, all right then, well, we'll find out. We'll be back anyway towards the end of the show with the result, and Herbert telling us why this has happened, and of course explaining why it relates to the real world as well. So do join us with that, and James will be there as well. Back to you in the studio.
Thanks very much, Derek. That's Derek, who is in the Naked Scientist Laboratory with Herbert Huppert and James F. Stathew, and they're going to be doing this experiment in about the next 40 or 50 minutes. If you want to have a go, get your fizzy bottle, get your sugar or your mint imperials, pour them into the bottle and tell us what happens. 08459 25 2000. First person through on the phone could win some fab prizes. We've got some Wiggly Wiggler vouchers, in fact £20 worth of those. And we've got a do-it-yourself worm starter kit, so you have a worm composter that you can build in your garden and it will produce worm juice for you, which is fabulous for your garden. OK, so get calling now with any solutions you may have to what happens when you do out this week's experiment, or if you want to have a go at our quiz, science fact or science fiction. It is, of course, The Naked Scientist, Dr. Chris and Dr. Kat. We're here with you live on BBC Local Radio right around the Eastern Counties, joined this evening by our team of experts to talk all about the science of supervolcanoes, tsunamis, quakes and shakes. If you want to ask anything about the geology of natural disasters and that kind of thing, we have Janet Sumner, Tiziana Rosetto and Tamsin Mather here in the studio. If you want to talk to them, 08459 25 2000, or send me an email, chris@nakedscientist.com. Now let's talk to someone who has really made history this week, because we've retrieved from space the world's first examples, pristine samples, let's hope, of a comet. And here to tell us about the Stardust mission, joining us in fact from Houston, and I hope Houston we don't have a problem, is Professor Don Brownlee. Good evening, Don.
Yes.
Good evening.
Good evening.
We nearly Houston did have a problem there. Tell us about the Stardust mission and what's it all about?
Stardust is a comet sample return mission. We went to a comet, grabbed a piece of it, and brought it home.
And how does it actually work? What was the nature of the mission? What did you actually do?
We flew for 7 years in space, traveled almost 3 billion miles. 2 years ago, we flew close to a comet called Wilt 2, which formed at the very edge of the solar system, not where Pluto is. And during the flyby, we took fabulous pictures of it, and we exposed a collector composed of this amazing material called aerogel, and collected thousands to millions of particles that impacted into this collector, folded up, and brought it home last week.
Why did you choose Wilt 2? What was special about that comet? Are there no others? Why did you select that one?
Well, there are a lot of comets in the solar system, but very few of them are places that we can get to. Most of them are very far away. Most of them are orbiting the Sun out beyond the orbit of Neptune. This one was conveniently located that we could get to it and fly by it at a pretty low velocity for interplanetary speeds and grab a sample and come home. But this comet also is interesting. It's only been in its present orbit since 1974. It now travels basically between the orbit of Jupiter and the orbit of Mars. But before 1974, it was a much larger orbit.
Why has it moved?
It moves because of planetary billiards. When comets get anywhere close to planets and they have gravitational encounters with them, their orbits change. Their orbits change all the time. They have very unstable orbits compared to the orbits of planets like the Earth and Mars and Venus.
So you've been flying this little capsule miles out in space. How do you actually control a spacecraft like that from such a distance?
Well, the spacecraft is controlled from a combination of Jet Propulsion Lab in Pasadena, California, and Lockheed Martin in Denver, Colorado. And we track it using a thing called the Deep Space Network, where it's a series of antennas around the world in Australia and Spain and the United States.
Is it radio signals that control it?
Radio. We send radio signals to it, and we get radio signals back. And we track it, so we know where it is. And we want to change its direction. We fire engines. We have 16 little engines, and we'll send a series of commands to fire those engines for some period of time and send it in a different direction.
Now, why is a comet so interesting to you? What can it tell you about things that you couldn't learn from Earth?
The most fundamental reason why we want to go to a comet is to learn about the origin of the solar system. The sun and the planets, which are the solar system, formed 4.5 billion years ago, and they formed from a disk of gas and dust, usually called the solar nebula. And the solar nebula was originally full of things like comets and also asteroids. It's also called planetesimals. And yet almost all of those bodies are now gone. They were either went into the planets, or they went into the sun, or they're thrown out in the galaxy.
And so this is almost like a time capsule, really, looking back at the 4.5 billion years that have gone by since our planets were forming.
Exactly. And at the very edge of the solar system, some of those bodies have survived since the very, very early beginning. I look on it like a cosmic library, if you will. The records of our formation, the original building blocks, have been stored out there for the entire age of the solar system, and we grabbed a piece of it, and we have it in our lab right now.
So really briefly, what sort of techniques are you going to be using for studying these particles? Presumably they're absolutely tiny. Are you just going to look at them, or what's going to happen?
Yeah, the particles are very tiny, but they're much larger than say, DNA, and we all know how much information is stored in DNA. With one DNA molecule, you can reproduce yourself. But we don't. These are not particles of DNA. They're particles of minerals and glass and sulfides and various kinds of organic materials. We actually have people all over the world using a variety of instruments to study the mineralogy, the composition, the isotopic composition, and everything that we can measure on the atomic scale. One of the ironies of this is to study really the smallest samples. You use some of the largest instruments. And in fact, the largest instrument used is the Stanford Linear Accelerator, which is several kilometers long.
Wow.
Just
Don.
an instrument.
No, sorry, Don, carry on.
Go ahead. Yeah, no, the Stanford Linear Accelerator is several kilometers long, but it's really, as far as we're concerned, it's an instrument in that it puts beams of X-rays on very small volumes and analysis, lets us determine the structure and composition of small particles.
Amazing journey.
OK, Don, thank you very much for joining us, all the way from Houston, but you're normally at the University of Washington, aren't you?
I am.
OK, thank you very much for bringing us up to speed on what you've achieved this week, and well done.
Thank you.
Thank you. That's Professor Donald Brownlee from Washington University, who has been involved as one of the principal investigators in the Stardust mission, which ventured to Wilt 2. It was launched in February 1999 and has recovered pristine samples, we hope, of that comet and brought them back to Earth for future analysis.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
So, every week we have a little podcast pick that Pedro selects. And last week we had a podcast on nanotechnology in healthcare from David Lemberg from Science and Society. And he's got another little bulletin for us this week, who's talking about our use of fossil fuels and how nanotechnology could possibly help us with our fossil fuel crisis in the future.
We all know that fossil fuels are no longer the way to go. Aside from the issues of being at the mercy of both market forces and hostile cartels, and rapidly depleting a non-renewable resource, global warming is now a well-documented fact. Energy has been described as the main problem for the next generation of scientists. Enter nanotechnology, in which many lines of research are working on both renewable and sustainable energy solutions. Photovoltaics refers to the conversion of energy contained in photons, that is, light rays from the sun, converting this into electrical energy that is usable by humans. This is an excellent solution. Use a fusion source that's safe, 93 million miles away. We need to decrease the cost by a factor of 3 and increase efficiency by a factor of 3. Depending on government focus and distribution of research grants, efficient photovoltaics will be available in 10 years. So this is very close. What about the hydrogen economy that's receiving a lot of press coverage? The idea is to use photovoltaics to convert the light energy into hydrogen and use hydrogen for mobile power in applications like transportation and computing. We know how to make hydrogen from electricity. We're still working on getting electricity from sunlight and still working on storage and distribution of hydrogen. The Holy Grail is to create a fuel without requiring any carbon at all, and this is 20 or 30 years away, and again, that is close, within our lifetimes. Thanks for listening. Next week we'll look at space exploration and nanotechnology.
That was Dr. David Lemberg with his podcast for this week. And you can find out more about nanotechnology and about David Lemberg's work at scienceandsociety.net. So that's his little internet site. If you've got your own podcasts, a minute and a half of audio interviewing a scientist maybe, or a science story, then email it in to us, chris@nakedscientist.com.
Thanks, Kat. It is The Naked Scientist, Dr. Chris, Dr. Kat. We're here with you until 7 this evening on BBC Local Radio right across the eastern counties, and we're taking your science questions. This evening's show is about supervolcanoes, tsunamis, quakes, shakes, that kind of thing, natural disasters. We have in the studio Janet Sumner, Tiziano Rosetto and Tamsin Mather. They're from, respectively, the Open University, University College London and Cambridge University, and they're experts on those things. If you'd like to ask them a question about anything to do with those fields, 08459 25 2000 is the phone number, or it's chris@nakedscientist.com on email. Now, let's kick off with Janet, because you work at the Open University, you're a volcanologist, but what does that actually involve? What's your job involving? What do you do?
Well, I do fieldwork, analytical and monitoring work on active volcanoes. Now, I started out life on volcanoes in the UK, which you'll be pleased to know, none of which are active anymore. But I've now moved on to work on active volcanoes. And what I do is I go out, look at volcanoes, but then I come home and I do stuff in the lab.
So what sorts of thing? Do you go and get a sample of a bit of lava or something and then bring it back to the lab and find out what's in it, or...?
Yeah, I've brought along one of the things that I collect to show you. It's, well, I don't know if you can take a guess at what you think it might be, actually.
It actually looks like a coconut shell, doesn't it? It looks almost like it's the size of a coconut. It looks like the kind of thing that falls out of a tree, but it's made of rock.
It does fall out of things. It falls out of the air. It's a volcanic bomb, and let me tell you how hard it is to get one of those on a plane these days, especially in your hand luggage.
It's like an enormous rock sherbet lemon. It's really heavy. I've got it here on my desk. So
but what actually is that? What is it?
That's a piece of molten rock that got thrown out of a volcano when it exploded, and as it travels through the air, it gets shaped into an aerodynamic form. Hence, it looks like a sherbet lemon sweet. It gets this very streamlined form. And what it is it's got a very chilled rind on the outside, and then the inside would have been filled with what was once molten rock. Now, because I can't use that stuff in the lab, because it's about 1,200, 300 degrees, it's much too hot for me to work with, I use something called an analogue. And I've also brought my analogue in to show you, and Kat's got it in her hand. We were talking about it earlier.
It is a Cadbury's cream egg.
What's left of it?
I hope it's still complete, because it has to be complete to do my experiments with.
I'll get you a new one.
I should hope so. It's basically the same kind of thing as a bomb, in that it has a chilled, brittle outer rind and then a kind of viscous, runny interior. And what happens is when these things come falling down out of the sky, they land on the ground and they burst open, and the runny molten rock comes out of the inside, and it all flows off together to form lava flows. And I'm working with Cadbury's cream eggs and glucose syrup to work how far these kind of lava flows can go.
OK, well, Janet, tell us a little bit about actually what a volcano is, because everyone's seen the pictures, we've all seen eruptions, but what's actually going on properly? If you were to write a geology textbook, what would you be saying is happening? What's happening on a sort of global scale?
Well, it's linked into plate tectonics. So basically most volcanoes occur where you've got either spreading plate boundaries, or one plate is being forced down under another. And basically what happens is either hot molten material from the mantle or nearer to the core of the Earth is rising up to the surface because it becomes very buoyant when it's warmer, or cold, heavy material is being squashed down and forced down under another tectonic plate, and that then goes down and melts and comes up through the boiling pot. So it's a kind of constant recycling motion. You can think of it as a pot of custard that you've allowed a skin to form on, and if you then heat that up on the stove, what will happen is the runny custard underneath will start to kind of convect and start to boil, and it will eventually split open the surface skin, and then new runny custard will boil out onto the skin and the surface.
Why do we have plate tectonics, though? Because if you take a look at, say, Venus, they don't have any on Venus. Well, not people, but Venus itself as a planet doesn't have any plates, does it?
Well, it doesn't really have plate tectonics, but what it does experience the same kind of overturning that the Earth experiences. It's just that Venus overturning happens on a global scale within a few tens to hundreds of thousands of years, we think, so that rather than individual plates jostling around, what happens with Venus is that the whole surface resurfaces itself within a short space of time, and you basically get a new planetary surface. Earth recycles itself on a slower scale than Venus.
So also the things you've brought in here, I have a pumice stone that looks a bit like it's been used on someone's feet.
Yeah, but hopefully yours.
Yeah.
There's been a distinct improvement in the smell in the studio this week. So
I've got
one
my
can only
shoes on.
Oh, that'd be why then.
That's why. And also this sort of big chunk of black glass. What have these got to do with volcanoes?
Well, I brought along the pumice stone because I did think that it might be the one bit of a volcano that perhaps many people would actually have in their bathroom and might actually have touched. So some of you, who do regularly scrub your feet with a pumice stone are probably touching a piece of a volcano. And the glass I brought in because that's also formed by a volcano. Watch your fingers on that. It is incredibly sharp and used to be actually shaped and used as cutting blades. And that is it's basically almost a form of silica. And because it cools so incredibly quickly, it literally forms glass. So those are just an example of the kind of things that volcanoes can produce. So it's tremendously varied.
It's a beautiful colour. Is this obsidian?
It is obsidian, yes.
Absolutely. It's really jet black. Fantastic colour.
Janet, can I ask you a bit about something that's always made me wonder? When you look in a textbook, you'll see this beautiful picture of planet Earth with layers peeled away almost like an onion. And they'll say, this is the crust, and then beneath that is this particular layer, we're into the mantle, and then we're into the outer core and the core. How do we actually know what's in there and what that structure is? How do we do that? Because it's obviously not practical to drill a hole 5,000 kilometres deep down through the Earth, is it?
Well, no, I think people have tried and gone some considerable distance, but we're never actually going to get that far. I mean, it's basically probably a question that my colleague sitting next to me can answer, because a lot of it's been done through seismic studies and by actually firing seismic waves through the structure of the Earth and then, based on the delay times, working out whether it's molten or whether it's solid rock. So
Tiziana, when we have an earthquake...
Yes.
Can scientists actually paradoxically use someone else's misfortune, they're having an earthquake, in order to learn more about what's happening inside the Earth and what the structure of the Earth is made
Strangely
from?
enough, it's already been done. There are two types of waves, or two main types of waves, which are generated when you have an earthquake. They're called primary and secondary waves, mainly because primary waves arrive first and secondary waves arrive second. Through the monitoring of these waves around the globe, we can basically see how long they've taken to reach the various locations on the Earth.
And so they travel at different speeds through different chemicals? They travel at different speeds
through different chemicals. But also we found that, for example, part of the core is liquid, because S waves, which are compression waves, sort of like sound waves, can't actually travel through, can't travel through liquids, and therefore are not visible on the other side of the planet.
So that's how we know what bits are liquid and which bits are molten, and which bits are solid.
Yes, it's surprising.
So earthquakes, they only travel around the surface. So if there's, say, an earthquake in Australia now, we wouldn't feel it because we're the other side of the planet.
Well, the second type, the different type of wave which is released when you have an earthquake comes from when the P waves and S waves that I've mentioned before actually hit the Earth's crust or any other surface, and they set up vibrations at the Earth's surface, which are what we feel as the strong ground motion. It's what causes the most damage to buildings and to, what causes panics amongst populations. And they attenuate, they die down quite rapidly with distance from where the earthquake has happened.
Are we any closer to predicting when an earthquake's going to happen? Because you've said that, it would be nice to know when it happens. Are we any closer?
Unfortunately not. I think the greatest progress that's been done so far is just to monitor the relative strains between along faults. So
why is it so difficult to have an earthquake forecast rather like a weather forecast? I know weather forecasts aren't known for their accuracy, so especially if you ask Michael Fish about hurricanes and things. But what's the difficulty that scientists encounter in trying to know when an earthquake might be brewing?
Well, an earthquake will generally occur along a fault, and we don't always know where the faults are. We only have about 100 years' worth of instrumental data on which to base our predictions. People have made studies of historical data looking at old news cuttings and historical records to try and find where earthquakes have occurred and assigning sort of sizes to those earthquakes. But essentially we don't have enough data to go along. We don't understand the Earth as well as we might. And we can't predict what time will lapse between one earthquake and the next. So that's our main problem.
You're listening to The Naked Scientist, Dr. Chris and Dr. Kat. We're joined this evening by Janet Sumner, Tiziana Rossetto and Tamzir Mather from Cambridge University. And if you'd like to ask any of them a question about the science of earthquakes, superquakes, super volcanoes, and how to build better buildings, which is what Tiziana's going to talk about in just a second, give us a call. It's 08459 25 2000, or you can email me, chris@nakedscientist.com. Remember, our kitchen science experiment is ongoing. Get a bottle of pop, pour some sugar or some mint imperials in, see what happens, and then phone up and explain the science. 08459 25 2000. Up for grabs this evening is £90 worth of wormery from Wiggly Wigglers and some vouchers, which you've also got, which you can buy things from the Wiggly Wigglers. They sell things like worms that will make your garden better, and they're on the show last week if you want to catch up with their programme. Go to nakedscientist.com and /podcast, and you can catch up with last week's show in which they talked about exactly that. Now, I've got an email for you, Tiziana, this is from Sam Freeman, who is in Santa Barbara in California. And she says, "Hi, Chris, I'm writing from Santa Barbara in California. I've just started listening to your show. I think it's great. Thank you very much." And she says she likes British accents because it gives her a chance to work on understanding the British accent, which and you're Italian, so now she can learn about Italian.
I don't know
accent.
about that.
But anyway, she says Santa Barbara, I've been told that Santa Barbara is the third most dangerous place to live in the United States because it's at great risk of being struck by a tsunami. I've taken particular interest in this branch of earth science. I was told that we're at great risk because there's a fault line that runs between our coastline and the Channel Islands west of the Pacific Ocean. Would you concur with that? And what is the mechanics of a tsunami?
Well, the mechanics of a tsunami, tsunamis occur from earthquakes where you have one tectonic plate subducting or moving below another continental plate, so generally between an oceanic plate and a continental plate. What happens is the deformation accumulated between the two surfaces. It's sort of if you have two pieces of sandpaper and push them one against the other, you'll see that at a certain point they'll move apart, and that's what essentially happens between two tectonic plates. In the case of a tsunami, it needs a vertical movement of the ground to initiate a disturbance to the surface of the water that's above it in the ocean. So there is a plate in the region, and it is a subduction zone. So it's possible that there might be a tsunami, but you can get movements of one plate relative to the other without large earthquakes happening and without large vertical displacements of the ground below happening due to that fault rupture.
Now, tell us a bit about what you've been up to in Pakistan, because you work actually as a structural engineer looking at buildings. And as the old saying goes, and I mentioned this at the beginning, it's not earthquakes that kill people, it's the buildings.
It is. If an earthquake happens in the middle of the desert, I mean, no one will get killed. Even if a person is standing there, they won't fall into the rupture. And, even though people think in films that you're falling in these big cracks in the ground. What does happen in cities, in urban areas, when an earthquake happens is that the buildings which aren't built to resist the earthquake loads, which are the majority of buildings, will collapse or be damaged and therefore cause life loss and economic loss to the city or the country. So I was in Pakistan after the Kashmir earthquake that occurred in October last year. And looking at the different types of buildings that are there, the different materials used, and how these buildings have been built, and generally getting an idea of what sort of damage is there and why buildings collapsed.
So briefly, what can you do to make a building earthquake safe?
Gosh, if you're building a new building, you can apply seismic codes, which will tell you how to connect or what sort of structural forms are best for resisting the lateral loads imposed by buildings. But if you have an existing structure, you'll have to see how strong it is, what size earthquake it can resist, and whether or not to intervene with sort of a strengthening of that structure.
And can you make sort of springy buildings? Aren't there some that have got big springs up the inside?
Base isolation systems are essentially, they look like gumdrops, except that they have like steel plates stuck between them. And what they do is they isolate the building above from the ground motion. So when the ground shakes, these gumdrops will absorb all the energy, and the structure above will stay relatively still.
You're listening to The Naked Scientist, Dr. Chris, Dr. Kat. We're talking this evening about supervolcanoes, natural disasters, tsunamis, earthquakes, that kind of thing. If you'd like to ask us any questions, 08459 25 2000 is our phone number, or you can email them in to me, chris@nakedscientist.com. We are, of course, live right across the Eastern Counties on BBC Local Radio. And, of course, if you want to catch up with any of the programmes we've done in the past, they're all archived on the internet at nakedscientist.com. And if you go to that part of the website, you'll see there's a radio archive, and you can listen to any of those programmes again. If there's something you missed and you think, oh, damn, I wish I had caught that one, you can download it and listen to it in your free time. Now, one of the other people we have with us this evening is Tamsin Mather from Cambridge University. Good evening, Tamsin.
Hi there, Chris.
Now, Janet works on actually the nuts and bolts of volcanoes, but you're interested in what comes out of them. Tell us about your work.
So I started off looking basically at atmospheres, and now what I look at is the effect that volcanoes have on atmospheres, or on our atmosphere more to the point. So my sort of like Janet, I go out into the field and take measurements of volcanoes. And,
so you actually have to wander around on erupting volcanoes?
Not erupting in the sense that probably most people think of, with a huge, big, explosive eruption column, but with a lot of gas coming out of them.
Have you ever been caught with your pants down, so to speak? Never been really close?
Never had. I've had ash falling on my head, but never anything bigger, which is fortunate, really. Tried to avoid that.
So the gases that come out of volcanoes, what sort of things are they? And are they very smelly? You get this idea of fire and brimstone.
There's definitely some fire and brimstone. You can often see the fire down in the crater below you. Cool. The brimstone, which is actually sulphur, you get a lot of sulphurous gases. So the eggy smell that people think of when they think about volcanoes sometimes, which is hydrogen sulfide. That's it. That's the one. Sulfur dioxide as well, which actually generally in the volcanoes I work on a more major component. And then you get acid gases as well. So like hydrogen chloride or hydrogen fluoride and things like that.
Pretty nasty.
It is. I was just, we were talking about it earlier, and a colleague went up with wearing a pair of spectacles, and his glasses got etched by the hydrogen fluoride. So this shows you, gives you a little bit of an idea about how corrosive these things are.
I was lucky enough, Tamsin, to be in Japan in the year 2001 for Christmas time, and I went to Mount Fuji.
Oh, yes.
And if you climb up adjacent to Mount Fuji, there's lots of hot springs there, and it absolutely stinks of bad eggs. That'll be the hydrogen sulfide. And there's a big sign which says, and actually very loosely translated from the Japanese into rather poor English, but it kind of says, if you stop noticing the smell of hydrogen sulfide,
run.
That's a bad sign. But presumably because once it reaches a certain level, it just abolishes your sense of smell.
Basically, yes. There's a window in which we're sensitive to the smell of hydrogen sulfide, and actually, once it gets above that window, that's when it really becomes quite toxic.
But why is analysing these gases actually useful to science? What can it tell us about science and how volcanoes actually work?
All sorts of things. I think the interesting thing is the different length scales on which volcanoes influence the environment. So there's the local effects, and for example, in South Pacific Island of Ambrym, which is part of Vanuatu, lots of the local residents show signs of fluorosis, so discolouring of their teeth and things like that.
But they don't need any fillings, though.
I wouldn't like to. I wouldn't like to comment on that. Not being a dental expert.
They've been eating Janet's cream eggs.
Too many cream eggs around volcanoes. But the fluorine levels there actually in the water which they drink are about 10 times the World Health Organization recommendations. But there's also global effects. That, for example, after the Pinatubo eruption, it shot up sulfur dioxide into the upper atmosphere, into the stratosphere, which the ozone layer. That's that part of the atmosphere. And you've got this aerosol veil, which actually Pinatubo went all around the planet and reduced the temperatures, the average surface temperature.
By reflecting sunlight back into space.
That's right, yes, yeah, exactly.
Because we also had some wonderful sunsets. I remember 1991, Mount Pinatubo in the Philippines, and I can just remember the sunsets, these beautiful golden orange sunsets every night for the whole year.
And
even the moon looked yellow.
Yeah, absolutely, and that was the aerosol, the small particles up in the stratosphere. And after a bigger eruption, I think the Tambora eruption, which was in the 1800s, 1815, I think, Janet. Yes, I got it right. There were some beautiful paintings done after that eruption. And so, no, you're absolutely right. It has some very beautiful aesthetic effects as well as negative effects.
You're listening to The Naked Scientist, Dr. Chris, Dr. Kat. We're live on BBC Local Radio right around the Eastern Counties. If you want to ask any questions about volcanoes, earthquakes and seismology this evening, 08459 25 2000 is our phone number, or you can email me, chris@nakedscientist.com. Let's take some calls. First of all, Alan's in Kent. Good evening, Alan.
Good evening.
You're interloping from Kent.
Yes.
Thank you for joining us. What's your question?
I was just wondering whether you'd allow me on coming from Kent, but you seem you have.
What would you like to know?
Yeah, the question is this. Over the hundreds of years that we've been removing gas and oil through the surface of the Earth and burning it in our cars and our power stations, would this have any effect on the stability of the Earth from an earthquake point of view, or even the way it spins in space? I mean, if you compare it to, say, an ice skater, who, when they pull their arms in,
they speed up.
Speed fast.
Because of the angular momentum. Yeah. OK, let's find out. Let's ask Janet. Janet, just briefly, because we are a little bit short for time, what do you think? Any risk of taking that much, say, include coal as well?
Well, I think the problem is that it sounds like an incredible amount, but if you actually weigh that amount up with the actual kind of volume of the entire globe, then it's incredibly small amount. So
it's quite literally a drop in the ocean.
Yeah, absolutely. You're looking at something that's the size of a pinhead compared to the entire volume of the Earth. So I think probably no, much less effect than we would think.
Alan, do you want a quick go at the quiz?
Yes, I wouldn't mind, yeah.
Okay, the Mohs scale is an old farmer's measurement for the height at which a crop should be cut down. Is that science fact or science fiction?
Can you just repeat the beginning of that?
Sure. The Mohs scale, M-O-H, Moh, is an old farmer's measurement for the height at which a crop should be cut. Fact or fiction?
Fiction.
You are quite right, yes, it's a measure of hardness of stuff. So diamonds are the hardest thing on the Mohs scale and score 10, and talc, so talcum powder, is the softest thing on the Mohs scale, scores 1.
OK, 1 out of 1, Alan. Next question. The nearest star to Earth is 62 Cygni. Is that science fact or science fiction?
I would say that's fiction too.
You're quite right, yeah, the closest star to our planet is our own sun. It is a star, it's about 100 million miles away, 8 light minutes.
Well done, Alan, you're in the lead at the moment. Great question, thanks for calling in.
Thank you very much.
The Naked Scientist, Dr Chris and Dr Kat, we're taking your questions, 08459 25 2000, anything on seismology, geology, volcanoes, earthquakes, that kind of thing. And let's have a quick chat to Les, who's in Over. Good evening, Les.
Hello.
Thank you for joining us on The Naked Scientist. What's your question?
I think I understand rightly that diamonds are produced by some volcanoes. Why is it some and not others?
Well, diamonds are forever, but are they from volcanoes, Janet?
They are certainly in response to volcanic action. Diamonds are formed in diatreme pipes, which are a kind of a very deep, steep-sided, very, very deep vent down into the earth. And that provides a very, very high pressure, particularly high pressure and temperature that diamonds need to form. So they're a sort of kind of drilling down effect rather than an exploding upwards and outwards effect. So think of a diatreme pipe as sort of drilling down into the earth at very high pressures.
So it's just purely the depth that they come from more than it being just a volcano then?
Yes, I mean, you definitely, you need the high temperatures, but principally you need the high pressures as well, and of course you need the fluidal material to actually form the crystals.
And then hopefully get them back out from the depths as well.
Yeah.
And then cut them.
Yeah.
And then give them to
and then put them on a lady's finger. Yes.
Do you want a quick go at the quiz, Les?
Yeah, I'll have a go.
A person with anemia has too few red blood cells. Is that science fact or science fiction?
Fact.
We've got people on form tonight. Yes, people with anemia don't have enough red blood cells. These are the cells that carry oxygen around the body in your haemoglobin.
We're talking about Vulcan earlier. Here we go, Les. Vulcanisation is the process by which rubber is turned into car tyres. Is that fact or fiction?
It's part of it, I think. Yes.
You're quite right, yes. You heat up rubber with sulphur, the smelly chemical we've just been hearing about, and other chemicals. It makes the long strands of rubber much tougher and harder, so you get solid tyres. Well done.
Thanks, Les. In equal first position, 2 out of 2.
Les.
Great having you on the show.
Bye.
The Naked Scientist, Dr Chris, Dr Kat. We're talking this evening about the science of geology. If you want to give us a call, 08459 25 2000. Might be able to sneak in a few more questions very quickly. In a second, we'll be talking to Elizabeth, who's in Colchester. It's BBC Local Radio right around the eastern counties. And you can email me too, chris@nakedscientist.com. Any science question on anything, pretty much. Elizabeth, good evening.
Hello.
What's your question?
How does the Richter scale work?
Whee! Come on then, Tiziana. This is definitely one for you.
Okay, the Richter scale, contrary to popular perception, is actually just derived for California, and it's a measurement based on the displacement measured on an accelegraph, a seismograph, sorry, which measures the displacement of the Earth due to the ground motion, and it's just a sort of an empirical measure from that.
It's logarithmic, isn't it?
It's logarithmic,
so in other
yes.
words, 10 on the Richter scale is not 10 times bigger than 1. It's much
bigger. I mean, if you take, for example, magnitude 5, that's and a magnitude 6. A magnitude 6 is about 32 times bigger in terms of energy release than a magnitude 5. But a magnitude 7 will be 1,000 times bigger than a magnitude 5.
Roughly how many earthquakes are going on all around the world today?
Oh gosh, hundreds probably, but some are made too small to actually be detected by humans, and some occur under the oceans or all over the world.
So, sorry to nick your phone call, Elizabeth. Can I ask Tiziana one more question before I ask you something? Would that be all right?
Yeah.
Why is it that we can have an earthquake in, say, Dundee or Dudley, which has happened recently in this country, but we're not near any plate boundaries? How does that happen?
Well, there are deformation stresses build up within plates themselves, and we don't fully understand how these events happen. But you do sometimes have small earthquakes happening in places which have never experienced earthquakes before, that we don't know have experienced earthquakes before. So Newcastle in Australia, for example.
Thanks, Tiziana. Elizabeth, do you want to go at the quiz?
Yes, please.
The Hubble Space Telescope was launched in 1992. Fact or fiction?
Fiction.
You're quite right. Was that a guess?
Yeah.
Good choice.
It went into orbit in 1990. Well done.
Well done. The Scoville scale is the measure of hotness of chilies. Is that science fact or science fiction?
Fiction.
No, it's actually true. You measure hotness of chilies in Scovilles, and the substance that makes them hot and spicy is called capsaicin. So the more capsaicin that's there, the more Scovilles you got, or Scovilles.
Well done, Elizabeth. Got 1 out of 2, so you're in second place at the moment, all right?
Okay.
Thanks for joining us on The Naked Scientist.
Thank you.
Thank you. Dr. Chris and Dr. Kat, we're here with you till 7 on BBC Local Radio, right across the Eastern Counties. If you have any science questions for us, 08459 25 2000. We're talking about the science of earthquakes and all that kind of thing this evening. Or you can email me, chris@nakedscientist.com.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
Good evening, it is The Naked Scientist, Dr. Chris and Dr. Kat, here with you until 7. If you have any questions on science, technology and medicine, and especially the science involving geology and volcanoes, that kind of thing, 08459 25 2000, or email me, chris@nakedscientist.com. Bill reckons he knows the answer to our kitchen science question. Hello, Bill.
Hello there.
You've been experimenting.
I did it, I popped out, come back in and heard it, and I thought, well, I'll just try it.
So, tell us first of all, remind us what the experiment was and what you found.
Right, put some lemonade in the bottle.
Right.
Either put some mint imperials or some sugar in.
Mm-hmm.
So I put the lemonade in the bottle.
Yep.
Made a little funnel.
Yep.
Put some sugar in. It fizzed over.
Yep.
All the sugar or whatever it came out.
Did it make a mess?
It made a mess, yeah. I did it in the sink, actually.
Oh,
so,
damn.
Yeah.
Never mind.
No, I wasn't that good. I did listen to what you said.
Oh, good, yeah. A man who followed the instructions. And so it fizzed over. So what do you think was going on?
Basically, the oxygen was being released.
Oxygen.
Or whatever, or something. The gas was being...
The gas was coming out, okay.
Coming out. I let it settle, and I tasted it, and it turned it back into, well, say water, but sweet water.
Yeah.
Had all the gases they put into it that makes lemonade.
Yeah.
Did it turn it... It made it flat again.
It gone flat, had it?
Gone flat.
Very good. Now, here's a man who's actually done the experiment. Fantastic.
Yep.
Now, we need to actually catch up with our guys in the lab and find out if you've got it right or not. Okay. So hang on the line, Bill. We'll join Derek, Herbert and James back in the Naked Scientist laboratory. See if you've got the answer right, and we'll be back with you in 4 or 5 minutes or so, all right? Stay on the line, Bill. Here we go. Derek. Has he got it right?
Welcome back to the Naked Scientist Laboratory, where I'm still here with Professor Herbert Huppert and also James, who's very kindly come to do this experiment with the lemonade and the mint imperials and the Smarties tube. So we've got it all set up, and all that remains to be done is actually to do it. So, Herbert, could you please remind James what he's got to do right now?
Right, James. So you're going to take the Smarties tube with the imperial mints in it, and you're going to pour it as quickly as you can into the bottle, and I might just help a little bit by putting my hands round it to make sure the imperial mints all go into the lemonade bottle and none end up in your stomach.
Oh, OK then. Right. So here we go. Herbert's kind of cupped his hands round the top here, but in they go. Tell us what you see, James. Whoa!
I see fizzy stuff all coming out of the bottle.
And how high did it go?
Quite high.
Yeah, I mean, that was quite something, I must say. And did you actually get all of the mint imperials in there?
No.
I mean, how many actually went in?
4 or 5.
Exactly, and we had 13 in that tube, and all we needed to do was put 4 or 5 in there, and we saw a massive amount of foam. I mean, this thing did not just foam over, this thing actually really, well, exploded all over us, and Herbert is currently drying his hands, because he was bravely cupping his hands around the top of the bottle there to make sure it worked. And it did, so congratulations to us, and very well done, James, that's excellent. So, Herbert, I mean, we need to know, firstly, why did this happen?
Well, the mint imperials allowed the carbon dioxide that was dissolved in the lemonade to come out of solution, because there's bits of sugar on it, and that acts as nice areas where the carbon dioxide can come out of solution. It comes out of solution as a gas, and as we all know, gas occupies much, much more space or volume than does the liquid equivalent. So suddenly there was a huge amount of volume in that container, and the only place it could go was out up into the air, about 6 inches, I would say.
And let's also talk about, the normal situation in a bottle of lemonade. So essentially you've got carbon dioxide dissolved in there. That's what makes it fizzy. But why doesn't it come out of solution so quickly and give us that effect without the mint imperials around?
Well, there are no sites that will allow the liquid to change into a gas. What the wonderful thing about the imperial mint or sugar or salt or even sand is that it makes for sites, sometimes called nucleation sites, where the bubbles can nucleate or the bubbles can form, and you get more and more of the dissolved gas coming out of solution through those little sites and then causing the big spout that we saw.
So the carbon dioxide, to get out of solution and into the gas form, really needs somewhere, a site, to form. OK, then now, also, we of course want to know how this all relates to volcanoes. So how is this kind of similar to some volcanoes?
Well, some volcanoes have liquid rock that have a little bit of water or carbon dioxide or other volatiles, gases like sulfur dioxide, in them. And as they rise up to the surface of the Earth, the decrease in pressure and the fact that there are little crystals in the liquid magma allow the carbon dioxide of the water to come out of solution, and then it's exactly as we saw. The only difference is, whereas in the lab we saw something about 6 inches, in real life these explosive eruptions like Mount St. Helens that you will have heard of can go some 10 kilometres into the atmosphere. That's about as high as a plane goes. And some planes have gone through the ash particles that have erupted in this explosive way.
There we go. So we've been making volcanoes in the Naked Scientist Laboratory, and I hope you've been making them in your kitchen too. So finally then, James, did you enjoy the experiment? How did you like it?
I thought it was very good.
OK, and you're going to go and tell all your friends to do it as well now and make a big mess?
Yeah.
Excellent. I'm very glad, and I'm indeed very proud of what we've achieved this week. So that's brilliant. Thank you very much indeed, Herbert. Have you enjoyed it?
Yes, it was great fun. I'm going to tell all my friends too.
Excellent. Good stuff. Messes everywhere, from academics to children. That's great. OK, then, thank you very much for joining us in the Naked Scientist Laboratory, and we will see you next week. Goodbye.
Thank you very much, Derek. Live there in the Naked Scientist Laboratory on the Naked Scientist, live on BBC Local Radio right around the Eastern Counties. Bill, sounds like you got it right, mate.
Thank you very much.
Well done. You've won yourself a worm composter. How about that?
Oh, lovely. Thank you
for trying our experiment, and I hope you actually felt it was constructive.
Yes, I did. Yeah.
Brilliant. Thanks for joining us on the programme.
Bye-bye.
Cheers. Got time now just to sneak in one quick question from Richard, who's in Colchester. Hello, Richard.
Hello.
Tell us your question. We're going to have to be really, really fast.
Why are there 2 or 3 waves in a tsunami instead of 1?
Tiziana, this is your bag.
Okay. Well, it's essentially the same principle that if you get a cube of sugar and drop it in your cup of tea, as long as you don't drop it in a cup of Coke instead, it sets up a disturbance in the water surface, and it doesn't reach equilibrium again immediately, so you get a lot of oscillations rather than just one. So you get more than one wave instead of just one.
So they all add together.
They all add together.
Bounces out and about.
Yeah, so just drop a cube of sugar in your tea and then you'll see the same effect.
Richard, does that make sense to you?
Yeah.
Great. Now, look, I'm really sorry, but we're very short for time. I haven't got time to actually offer you a go at Science Fact or Science Fiction this week. All right, so if you want to give us a ring next week and we'll see if you can have a go at the quiz.
Okay.
All right, it's a great question, though. Thank you for joining us on the programme. Thank you. Good night.
Bye.
You've been listening to The Naked Scientist. I've got just a few seconds to say a terrifically huge thank you to Janet Sumner, to Tiziana Rosetto and Tamsin Mather from Cambridge University. Thank you, Tamsin, for coming in. Thank you to all of you for doing a wonderful job this evening and making the science of seismology so exciting. Next week, we're talking about space science, and we're going to be joined by Ian Sanders to talk about meteorites, and we're going to be talking to Maggie Adarin about space science, and she's making a satellite. She's actually involved in making a satellite that's going to be used to predict Earth's weather. So, who's won the quiz this week? Well, our winners are Alan, who's in Kent, Les is in Over, and Bill won our kitchen science. Have a great week, and we'll see you soon.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.